everybody, it's me, Ladyada, and I'm here at Espressif DevCon. I want to talk a little bit about some of the work that Adafruit and all of its amazing team members have been working on over the last few years using ESP Espressif chips, and also some of the stuff that Adafruit's been selling and how and why we've been doing CircuitPython, which is the topic of today's little chit-chat that we've recorded here. What Adafruit's done for the last 15 years is sell a lot of open source hardware. That means that I design circuit boards using Espressif chips, for example, and then we sell the assembled boards, tested, ready to go with documentation. We also release firmware, software, and hardware under open source licenses, usually MIT or BSD license, so people can take that code, that hardware, remix it, and reuse it into their own products or projects. This is great for the engineering and development community because they get a little bit of a head start. They have known working schematic, known working code, and as we'll see, there's actually quite a bit of the pieces and parts that make up CircuitPython that even if you're not using CircuitPython, you might be interested in as a developer of ESP32 or Arduino or MicroPython. So I thought we'd first start off with just talking a little bit about how we got to CircuitPython, because I think it's an interesting story. A lot of people are like, why do we need interpreted languages? Isn't assembly good enough? Why don't we just write everything in Tensilica or ESP32 or whatever low-level code? And I think one thing that's interesting to remember is that when the first Espressif chips hit the maker developer market, not just the Wi-Fi chips that were meant to be used in a Linux system, but actually development boards, the ESP01 and the ESP8266 modules, they often came with either AT firmware, which meant that you would control the ESP chip itself as a Wi-Fi coprocessor. You'd send it commands like, AT Wi-Fi connect, AT socket open, etc., and you would connect to a Wi-Fi website. You would be able to send and receive data. You could even set up a little server, open up sockets, UDP, TCP, etc. And then, people started with that. And we actually had a couple of guides showing how people could use something like an Arduino Uno, connect over serial to an Espressif chip to, the wider world for Wi-Fi. It was extremely affordable. And then what we saw actually, which is a little interesting, is some folks, I'm assuming that they were at Espressif, but to be honest, I should have looked this up before I did this video. They ported the Lua scripting language to the ESP8266. And this was really interesting because the 8266, is this Wi-Fi processor. It has the radio built in, but it also had enough RAM and flash, built-in memory, to be able to run a scripting language. Yes, you could write code in C or an Arduinoese, but there was some benefit to Lua, which is a scripting language that's often used by game developers to automate and run within their games engine. But it was it's a scripting language that allows you to write code quickly. The script is run within the virtual machine that's running on the ESP8266, and I think that having Lua available was what kind of prompted a lot of people to think about, what if we used interpreted languages instead of just compiled languages like C or Rust or assembler or C++ or whatever your favorite compiled language is. So in 2016 we saw a Kickstarter by Damien George, who is the author of MicroPython, and he had been working on MicroPython, a small microcontroller-based Python interpreter for the STM32 series chips. And the STM32 series were, of course, Cortex chips. But he was really interested in this idea of the 8266 being available, has Wi-Fi, and how this could really be a powerful way to introduce interpreted Python on a microcontroller while also bringing in IoT. And for reasons I'll show later, it's a really, really good match. So when he did this Kickstarter, first off, a lot of people got very excited. It got a lot of funding. We chatted with Damien and actually contributed, not just by funding him, but also we wrote a whole bunch of tutorials and guides for MicroPython. because we thought it was really neat to see, like, okay, you've got this powerful chip. It's so powerful that maybe you have a little bit of extra processing time and speed, and it's interpreted so it's slower, but maybe it's okay. Maybe you're not CPU bound as much or memory bound. Having that run on ESP8266. So we actually ended up writing a bunch of tutorials and a bunch of guides and a bunch of libraries for MicroPython. People still use them for the 8266. And, that was super cool and great for a very long time. And we still think it's, MicroPython is definitely a really good alternative to CircuitPython. CircuitPython is not meant to replace MicroPython. They live side by side. The goal of CircuitPython is to make things easier for beginners, because we have a lot of customers who are students, or they're beginning engineers, or they just want to get started really fast. And so our goal is to make things really, really easy and unified, have the same code run under CPython as CircuitPython. All platforms should have the same API. So a couple of these engineering decisions that we made were incompatible with MicroPython, and this is why we ended up going with CircuitPython. We renamed it because we didn't want to cause any confusion. That said, we still commit code to mainline MicroPython through pull requests, and vice versa. We like to keep up. And we collaborate all the time on stuff. Like async IO is one of the ways to do asynchronous, not threaded, but multiple threads of control type computation on CircuitPython, MicroPython. It's something that we chat with MicroPython to collaborate with. So, one of the questions that we do get a lot, is like, why would you want to have an interpreted language? You're going to be using so much more power. You're going to be using so much more memory. And I guess for us, or at least for me, I've spent a lot of my life in tool chains. I have this Windows computer here, and it's got 8,000 tool chains installed on it, from TI, from STM, from Atmel, Microchip, from Espressif, multiple versions of the IDF, Arduino, multiple versions. And when I think about when I started with electronics, the way you would program, I programmed PIC microcontrollers, and a lot of people watching this probably started with these early microcontrollers. Flash memory wasn't yet affordable, so they were UVEEPROM programmable. And so whenever you wanted to write code, which was often in assembler or in a very, very low level C, you would have to write your code, you'd compile it into a binary, which didn't take that long, but then to upload the code, you'd have to literally remove the chip from your board. You'd put it in a UV eraser, you'd wait 10 minutes, take it out, and now it's erased, and then you could program it with your code and then you'd test it. So every cycle of compilation and testing took 10, 15 minutes. And if you tried to rush through the UV process, if folks remember, you'd end up not actually erasing the whole chip. You'd have to kind of start over because it wouldn't verify right. So one of the things that was really nice about moving from UV to Flash to bootloader type development, such as with Arduino, is that cycle of coding, compiling, upload, testing, debugging is getting faster and faster and faster. What was 10 minutes, 15 minutes with UVE proms, once you got to Flash, okay, maybe it's 2 to 3 minutes, and then, and you'd have to physically maybe do some connecting or bootloading. When then with Arduino, with auto reset and auto bootloading, maybe it would be even faster. It would be 30 seconds to a minute. And that really sped up the ability for people to learn and iterate on their designs. However, and I think, this is something that people who work with the ESP IDF know, even with Ninja and really fast makefiles and configurations, it still does take quite a while to compile code and then upload that to Flash. I mean, Flash memory, it actually becomes a little bit of your time bound because you have to erase blocks, and that takes time, and then you have to reprogram the blocks. So unless you have some sort of really cool mapped memory Flash, your code goes into a section and you don't have to erase the whole thing, it still does take quite a bit of time to do a development cycle, even if your compilation is now optimized, which I know people have been working a lot on, and I commend them. It's much faster to compile code for Espressif than many other platforms. But that said, what if instead of 30 seconds it was 2 seconds? What if it was instant? What if it was something you could do from your web browser? What if it was something you didn't even have to install a tool chain for? And that's kind of the goal of CircuitPython is, yes, you're going to be a little slower. Yes, it's going to take more memory. Yes, if you want optimized, very speedy parts, you have to write that in C, and you have to kind of build it into CircuitPython, which I'll show later. But if you're doing prototyping, development, or you just need a very fast cycle of iteration, especially I've noticed with doing robotics, anything when you have to do heuristics or calibration or customization or user interfaces, that fast iteration cycle in CircuitPython is like really joyful compared to the compile, upload, erase flash, program flash, open up your terminal, debug. So we're going to go look at that process. I also want to just show really fast some of the hardware. So let's go to the overhead, and I'll just quickly show off some boards just so people know what we're talking about. So this is, Feather board, ESP8266 and ESP32. People really like these. And then, we've now got boards that have built-in screens on them. This is at ESP S2. This is a board that has built-in battery and ESP S2. And then on the top, there's an e-ink display. This is another ESP32, classic, not the S series. We also have S3 and C3 in addition. So let's now that we've introduced everything, we've just explained what we're going to do, let's actually show what it's like to use CircuitPython on the Feather ESP32 and ESP32 S2. Okay, so everything that you need to play around with CircuitPython is available on circuitpython.org. That is the website that I'm at right now. And we have tutorials linked from here, but most people want to get started immediately by going to the downloads page. And the download page has 340 different boards, and not just stuff from Adafruit. We support all sorts of makers. Anyone can submit a PR to add support for their board, and the board definition, you just need to have your own USB VID and PID. The board that we're going to be playing with today is the ESP32 S2 TFT, which is this one. And we have usually a stable release and kind of a cutting edge release. Right now we're working on CircuitPython 8.00, which is like our big Espressif release. We're adding a lot more support for ESP32 boards, including the classic ESP32. You can download either binary, which is, you would burn that directly with ESP tool, or you can download a UF2. So a UF2 is a file format that we really like to use that is compatible with mass storage bootloaders. So if we go to the overhead real fast, I'll show off the mass storage bootloader. Because the ESP32 S2 has native USB, which I think is amazing, and so does the S3, there is the ROM bootloader, and then on top of that we install what we call the UF2 bootloader. And the UF2 bootloader takes advantage of the mass storage interface over native USB to allow you to drag and drop a file. Why? Because there's actually a lot of people for whom installing ESP tool is a bit of a struggle, especially if you have an older Mac and the Python is 2.7 and it's got to install Homebrew. Basically, it's like if you can get them to run the TNEF2 bootloader, it's very easy to upload new code. You just double click the reset button and drag a file on. So if you go to the computer, the Feather now shows up as a disk drive. It contains current UF2, which is the current firmware, index HTML, which if you double click it will take you to the page, and then info UF2, which tells you, what version you're running of the TNF UF2 bootloader. And then I can just take that file. Hold on. I can take that UF2 file. I just drag it on, and then it'll burn the bootloader. It takes some time, it's erasing the flash and reprogramming it. And then when the board comes up, which it will in a moment, it shows up as a disk drive called Circuit Pi. So if you look on my computer, there's one disk drive here called Circuit Pi. Again, taking advantage of native USB. You might be wondering, wow, this native USB stuff is really cool. What if I want to do it? Well, TinyUF2 is a USB low-level stack that is completely open source and runs on a variety of different processors, including Espressif. Espressif uses it in the ESP IDF. So MIDI, somebody actually just added U2F, mass storage, CDC, HID, host if the chip supports it, all that stuff. There's example code in the TinyUF2 and TinyUSB GitHub repos. TinyUSB is the underlying USB stack. TinyUF2 is the UF2 mass storage bootloader built on top of TinyUSB. And this is developed by TAC, who is an Adafruit developer. So even if you don't use CircuitPython, please do check it out because it's a really awesome USB stack. It's one of the only ones I know that is completely open source, freely licensed, and available for multiple processors. Okay, back to our CircuitPy drive. So again, for usability, one of the things that we really like is having the storage for code and files and accessories and everything you need for your development as mass storage. You know why? Because mass storage is the most universal USB interface. Everything supports it, including Android, Chromebooks, old Macs, new Macs, Linux, Windows. Even CDC can sometimes USB CDC for serial command control. Sometimes you do need a driver on some computers, but mass storage is forever. And so it makes it really a great way to make sure that no matter what platform people are running, they don't need to have any special tool chains because you can just double click the code.py file and then edit it directly. So I'm going to open this in Atom. So because the ESP chip has native USB, it has multiple endpoints, we actually show up as a composite device. We have mass storage, again, HID and MIDI as optional, and then CDC for the REPL. The REPL is the interface to the Python virtual machine. You can run commands within the REPL, so common one is you just type in 1 + 1, and it's like 2. Or you can import a library, and then you can do what's in that library, and then you can say, oh, what's the OSU name, and it's like here's info about your board. So you can use the REPL to play around with. I think it's good for just very basic, like how do you index within an array, and then you want to try built-in functions within Python, like, oh, what's this math command for exponentials or whatever. But for the most part, what you're going to do is put your code in the code.py file. And Scott, who's the lead developer for CircuitPython, and so came up with all the API and interface decisions, a lot of which were based on usability, had this idea, which at first I was a little bit shocked by. And he said, oh, I want to make it so whenever you save the code.py file, it will rerun the virtual machine. And I was like, that goes against everything I know as an engineer, but okay, let's try it. And actually, it's kind of cool. So what it means is that I can really quickly do development. So like, I already have this example code ready to go. I have a code.py file with a bunch of code in it, and I'm going to drag and drop all the files, and then, we can go through the details behind them later. So to put your code and your assets, library files, fonts, images, whatever accessories you need for your code, you just copy it on over mass storage, and then later I'll show what you do if you are like, what if I have a chip that doesn't have native USB, like the original ESP32? Don't worry, that's also possible. Okay, so let's replace all the files, and this is using the built-in 4 megabytes of SPI flash. We partition it out so you have, some of it's for firmware, some of it's for over the air, and then we have like a megabyte or so available for code. So let's close this and open the code. this is the code I'm running. So, there's all sorts of libraries you want to install, SSL and Wi-Fi and display support. One thing that's kind of neat is if we go to the overhead real fast, the REPL, if you have a computer, if you have a microcontroller board with a built-in TFT, you can actually, as I'm typing into the REPL, hello, the same output echoes on the TFT. So it can be nice for debugging. You can see like what you're doing. All right, so let's go back to the computer. So in my code, what I'm going to do is I'm going to connect to the GitHub API over HTTPS. Having TLS 1.2 support is really awesome in the ESP32. And it will load up a bitmap and it will load up a font. This is one of the things that was really powerful about CircuitPython. Things like, I just want to display a bitmap, or I want to parse a PCF standard format font and use it for my UI. It's trivial and it's built into CircuitPython. We kind of like to have as much stuff built in for these kinds of advanced graphical interfaces. I also have like audio playback built in, stuff like that, like wave playback. It'll connect to the SSID, which is defined in a different file called secrets.py. We like to have the configuration in different files so that people don't commit both files if they're working on it. Obviously you don't want to have your SSID, your passwords, or your GitHub token mixed in with the code. But it's very easy to load as a separate file off of the file system. And then it can open up a socket pool, create an SSL context, and then use requests, which is a very standard Python library that's actually originally was written for CPython on desktops, but we kind of made a very lightweight version that runs on microcontrollers that can use authorization tokens if you want to. It can add in stuff into the request, sort of like curl, to authenticate you or set permissions or what have you, if you have to send tokens back and forth. And then what's really neat is that JSON parsing is built into CircuitPython, and it's also stuff like string parsing and error handling and dealing with binary hex data, and then you have to parse it. All that stuff that's really, really frustrating to do in C and C++. I know it's possible to parse JSON or CSV files, but I just really hate doing it in C. It's always, either you're doing it by hand and you're kind of stumbling around, or you're doing it with a library and it's like this massive thing, and then, even then, one wrong comma or wrong quote, you'll never figure out what the issue is, whereas the built-in JSON parser we have in CircuitPython is really reliable. You get the JSON, and then you just, I'll show after I get this running, you could print out the JSON, and then I can print to the text REPL the output, and then display on the display the string, the text. So this is going to look at the number of stars that we have on the CircuitPython repo. So what's nice is that I just hit Control D in the REPL, and you'll see it's going to connect to the internet. It gets an IP address, it fetches the JSON, it has the display, it shows me the number on the screen, and if I go to the overhead, it'll show the number of stars. So, that's a project I already had ready to go. And so, again, the power is now I want to really quickly iterate. So let's show what it's like to quickly iterate. So let's go to the computer. So first up, I was connecting to the Adafruit repo, but I actually want to do Espressif ESP32 instead. And then second, and I can save this and it immediately starts running. So while it's running, I can also say, well, I have this background image is what I'm displaying, but I actually want to display this background instead, because of course it's no longer displaying the CircuitPython demo. So the first change ran already, and it says, okay, yeah, the number of stars for this repo is 9,000 something. Cool. let's change the background. So I'm going to save that. It's going to rerun immediately. And then if we go to the overhead, you'll see the graphics has instantaneously changed. And the reason you're actually not seeing the text is because it's white. So, oops, bug. Let's go fix it real fast. On the code over here, we're going to make a text label. Let's make it red instead. And then let's also change a different font. I've got the impact font. So I'll change the font. And then when we rerun it and go to the overhead, you'll see this time my live demo shows the text. Now, of course, I can, the text is in the wrong location. I can tweak the X and Y coordinate. But you see how fast it is. It's like the code, once I've got it, I can make 4 or 5 changes in about 30 seconds and instantly see the output. So that's the goal of CircuitPython, to make that iteration cycle so fast, it's actually enjoyable to code. Okay, finally, we're going to look at what happens if you don't have native USB and you don't have a display. Of course, it's a lot easier to do Wi-Fi development if you've got all that file dragging and dropping. For the CircuitPython 8.00 release, one of the things that we've added is this Wi-Fi web workflow. So this is an ESP32, the classic, does not have native USB, and it doesn't have a display on this feather. So let's go to the computer. So for this board, we do have a download for it, and you'll notice that CircuitPython 7 isn't available because this is new with 8. You download a bin file, because again, there's no TinyUF2 drag and drop bootloader. And then you'll use the ESP web flasher, which is written by Melissa here at Adafruit, which allows you to use web serial to upload code. And it's basically like ESP tool, but in the browser for Chromium browsers. And then once you've uploaded it, you can also configure the Wi-Fi SSID. And what's really neat is you can then go to http://circuitpython.local, and this will show up. This is running on the CircuitPython board itself. It has a little miniature web server that allows you to, first off, get information about the board and what the IP address is. And then there's a built-in, again, very simple serial terminal. So I can type in commands, which you can see now scrolling past my screen. And then there's also a file browser that you can use for, again, very basic, you want to upload files and you want to, say open your code.py and see what code is inside of there. But if you want to do some real development, we also have a web-based full code editor. And the full code editor, it connects to your computer via sockets, web sockets. You can open up your code.py file. It's got hello world here, but let's say I want to have some neopixels going on. I will copy and paste this code, save this as code.py, and it uploads the code to the ESP32 feather. And then let me kick it. When you restart it, when we go to the overhead, you'll see blinking neopixels. So, file management and serial terminal and code running, all that you can still do with the CDC port that you've got. But if you want to not have to muck around with using a special IDE, you can use our web-based Wi-Fi serial interface. So I think this will still make it really easy for people, even if you don't have native USB, which we do like, but there's still thousands of people with the classic ESP32, which we want to support. So that's kind of an introduction to CircuitPython, the ESP32, S2, S3, C3, and the native are supported. I think it's a really great match. The ESP32 is so powerful. IoT, I think, is a great match for CircuitPython. This is a great way to get started with development if you've never done IoT development, and it's a great way to iterate your design before you go into production.